I'm going to give you a sense of what kind of problems you are going to encounter with your review, and I hope you find them easy, and they are really easy. So, for example, this problem is dealing with light intensity. So, if light intensity is given at certain place, you should determine the total energy that enters a window with certain area during certain time. If the area of the window is given, either the area is given or two sides of the rectangle, you can determine the area. You should use this formula that intensity, by definition, is energy divided by area divided by time. That's it. And from here, if intensity is given, the area is given, window of area A in 1 minute, then energy is intensity times area times time. Okay? If the time is given in hours or in minutes converted to seconds, this should be square meter. Okay, consider a concave mirror. This is reflection. The radius of curvature is given, and the magnification is given for this concave mirror. You should find where the object is, object distance, dO. So the radius is given, you immediately find the focal length. Focal length is 1/2. Concave mirror, the focal length is positive or negative? Okay, find because in formulas we have focal length, we don't have the radius. Okay, determine the focal length, and then I'm asking to find the object distance. So you know the mirror equation, inverse of focal length is inverse of image distance plus inverse of object distance. You could determine the object distance from here if you knew the image distance, which is not given. However, the magnification is given. So it means that you can use magnification somehow to find the image distance. So this is magnification is negative pi over dO, right? And from here, image distance is negative n times dO. And n is given. This is negative 1.5 times dO in this case. Okay? If you replace the image distance in this equation with this, you get one equation with one unknown. Because you found the focal length. Here you place negative 1.5 dO, and you have find dO from there, one linear equation with one unknown. So this problem is about total internal reflection. This is the situation. You have interface between air and water. You should know refractive index of water is 1.33. Okay, for air it's 1. So this is what happens. At certain angle between the light is incident in water. It hits the surface at certain angle relative to the surface. And it undergoes total. This is the angle at which light goes parallel to the surface. Basically, it's related, and this occurs at the critical angle. Right? Critical angle of incidence. Okay, if this is the angle of incidence, theta incidence, basically this is the critical angle. If incidence angle is this or larger, then in that case you have a total internal reflection. So in this equation, you should find the angle alpha. Basically, this corresponds to the critical angle. You should use the formula for the critical angle. Okay, sine of the critical angle is n2 over n1. n1 is the medium where the light is incident. Okay, basically this is water, this is air. Okay, determine angle, this angle, which is inverse tangent of this ratio, and don't forget to make sure that you determine angle alpha. Okay, as you can see, if incidence angle is critical angle, then alpha is 90 degrees minus this critical angle. Now we have a lens, and the focal length is given, and the object distance is given. You should determine the magnification. This is similar to that mirror equation. Immediately when focal length and object distance are given, we can immediately determine the image distance using the thin lens equation, which is the same as the mirror equation. Is 1 f equals 1 over 1 plus 1. Thin lens equation from here determine image distance, because the other two are given. And then now you know the image distance and object distance. Use the magnification equation to find the magnification. So magnification is image phi divided by object phi, which is equals negative image distance divided by object. So you can see that these are really straightforward, mostly one-step or two-step problems. So double slit problem, double slit. There's, I believe there's one problem from chapter 27. Double slit problem, let's see what is given. This is the double slit, okay, 1 and 2. So the distance between the slits is given, the length of the slit is given. Now you have the height, h. H is the distance from the center, vertical distance where fifth bright fringe is found. Okay, fifth number 5, it tells you n equals 5. Huh? Fifth bright band or bright fringe is occurs at a certain distance which is given. You should find the frequency. Okay, this is bright. Bright fringe tells you that you should use the constructive, the condition of constructive interference. Because at that point, you see bright spot, at that point you have constructive interference. Then this is the equation, the formula for constructive interference. You should find the frequency. Okay, here this equation gives you relationship between d, the angle, the order of the fringe, and the wavelength. You are trying to find the frequency. You should convert the wavelength to frequency. So the speed of light is f times lambda, convert lambda is c over f. So you can convert lambda c divided by f. Then from here, the frequency is This is the order of interference, which is phi. Okay, this is the speed of light that you know. N is the order, which is phi. D is given. And you can find the angle from the geometry. So L and H are given, the distance to the screen and the height. So tangent theta is H over L. We find theta from this relationship. Theta is inverse tangent of that ratio H over L, and both of them are given. So basically, this is again, I can say, one-step solution. It's a price for constructive interference. This is the equation for constructive interference. You are looking for frequency, convert lambda to frequency, and then solving for frequency. When you solve, you find that you don't know the angle, but look at the problem again. The geometry is given from which you can determine the angle. So here we have a equation about the magnetic field created by current and magnetic force acting on a moving charge. So let's see what is given. You have a wire which has a certain current in it. And there is a charge at certain distance r. And this charge is moving parallel to the wire. This charge is moving parallel to the wire. The charge of this particle is given, its velocity is given, its distance from the wire is given. And when it moves this direction, so the current creates magnetic field, right? Now you have charge moving in a magnetic field, and there's certain magnetic force which is given. You know that when this charge moves with this speed, a distance r from the wire, it experiences magnetic force which is given. You should find the magnetic field created by that wire at that point, and you should find the current, okay? So, you know the force, so basically you can use the formula for magnetic force acting on moving charge. But the charge times velocity times magnetic field times sine of the angle. Sine of the angle between velocity and magnetic field. So let's try to find what this angle would be. You have a wire, and magnetic field created by current in the wire is circular, right? Everywhere the magnetic field is perpendicular to the wire. When you use your right hand tool, your thumb goes along the wire, the current, upper of this wire, magnetic field comes perpendicularly out of the picture. Lower, it goes perpendicularly away. So at this point, the magnetic field goes perpendicularly away, and this is B. What is the angle between B and B? It's 90 degrees. Therefore, this goes away. Sine 90 degrees is 1. So you can ignore this sine theta, it becomes 1. And from here you can determine the magnetic field is the force divided by Q times B. That's it. Sine theta becomes 1. Okay, once you find the magnetic field, part is find the current. So you should use the formula for magnetic field created by a wire at certain distance r. Okay, this formula is B equals mu0 times the current divided by 2 pi r. Okay, from here find the current. Okay, let's see if you can do this. B, you just determine the magnetic field. The distance is given, and this is going to be given magnetic permeability. So two steps for parts A and B.
What is the symbol saying for your B formula?
What's that?
Okay, when you have B equals F over Q, what is the bottom? Is it equal?
Thank you.
That's nothing. I tried to raise it. Okay, let's consider now use electromagnetic force. So we have a rectangular coil which contains like 500 turns. That number is going to be given n. N is given, now this is square actually. Square, the size of this square is given b, and something should change in order to have electromagnetic force. So magnetic field is perpendicular to the surface of this coil and is changing from 120 millitesla down to 440 millitesla in 4 seconds. In 4 seconds, it changes, decreases from 120 to 40 millitesla. Find the magnitude of induced electromagnetic force. So we are using Faraday's equation, which says induced electromagnetic force equals number of turns times change of magnetic flux with time. And also a formula for flux, which is E A cosine phi, where phi is the angle between magnetic field and normal to the surface. So magnetic field is perpendicular. In this case, magnetic field is perpendicular to the picture, and normal to the surface is perpendicular. So the angle between B and normal to the surface is 0, and cosine 0 is 1. So this goes away again. So now you can write this formula replacing flux with B times A. However, if A is constant and B is changing, then change of flux is determined by change of magnetic field. So you can write induced electromagnetic force equals N times, I'm replacing phi with this, but A is constant. A is not changing, B is changing. This would be delta B divided by delta T, and I continue it. And what is change of magnetic field? Final value minus initial. Final is 40, or I can write 40 minus 120. It says millitesla, right? I should multiply by -3, milli. This many Tesla, this is the change, but this occurs in 4 seconds. 4 seconds. Okay? Basically, here we have negative 80 times 10 to -3 divided by 4 times A is the square, D times D is the D squared, N is given. If you get a negative number and the problem of the magnitude, you can just provide a positive number. If you give a negative number, that's okay. So straightforward problem, again, one step. RLC circuit. As you can see, I'm just trying to see if you have the basic knowledge, very fundamental. For example, RLC circuit, you have alternating current source, which has certain frequency. The frequency is given, and the resistance, the inductance, and capacitance are given. You should find the impedance, first of all, and then you should determine if you are allowed to change the inductance of the inductor. What inductance you would choose to have maximum possible current. Basically, maximum possible current occurs when the resonance takes place. Okay? You should, okay, let's do part A. Find the impedance. You remember the formula for impedance? C equals square root of R squared plus. Okay, formula for impedance. And you should also know this is inductive reactance, capacitive reactance. Okay, everything is given. F is given, L is given, C is given. You can determine this and this R is given. Okay, for part one, very simple. Now part B is talking about maximum current. Maximum current corresponds to resonance frequency, and the resonance frequency is given by this formula. You should determine basically at this frequency, either you can keep the frequency and change this or both of them, okay? Or at this frequency, you can change any of these, either inductance or capacitance, which is basically occurring when you are tuning your radio, you are changing either inductance or capacitance to get maximum current at certain frequency. Now this frequency is given, right? This frequency 2 pi. Okay, that's 2 pi wave 0 is 1 squared equals 1 divided by LC, right? Just take the square of both sides and use the formula omega equals 2 pi f and solve this for either for inductance or capacitance. I can ask if you keep the inductance the same, at which capacitance you would get maximum current. You can solve it either for L or for now we consider another circuit with constant direct current source. This is the situation. You have 3 resistors and 1 capacitor connected as shown here. You should find the charge. You turn it on and let it go for some time. So this capacitor gets charged totally. So you should find the charge on this capacitor. So you can determine the charge on this capacitor using this formula. By definition, the capacitance is charge divided by voltage. If this is point A, this is point B. If you the capacitance is given, the voltage is given, and all resistances are given. you could find the charge on capacitance, which is C times V. If capacitance is given, you need to determine the voltage between points A and B. Okay, that voltage drops on this resistor to R. It is also the same voltage that drops on the capacitor. So how can you find that voltage? So you can determine the current. Okay, the current, total current, which is the same in all these three resistors. Two resistors are connected in series, they have the same current. Once you find the total current, that's the current in each of these resistors, including these two R. When you find the current into R, you can multiply that current by the resistance to R. Current times resistance is voltage. You can find the voltage. And then multiply it by capacitance, you can find the charge on each plate of this capacitor. So the total resistance R total is, because they are in series, is 4 R, 2 R, and 1 more R. This 4 R. Now the current is total voltage divided by total resistance. Okay, this is the current flowing in your circuit, including this. So what is the voltage on 2R? On 2R, the voltage is total current times 2R. If you replace R with V over 4, R comes 2R. This R goes away. It becomes 1/2 V. Okay, it turns out in this situation, when the relative values of R are this way, this is 2 times more than this, then on that resistor gets 1/2 of the total voltage. So that's the same voltage as on the capacitor. Okay, multiply that voltage by capacitance, you get the charge on the capacitor. Total current, which is the current in this resistor, current times resistance gives you the voltage between A and B. And that's the same voltage as on the capacitor. Multiply voltage by capacitance, get the charge of the capacitor. Again, charge is moving in a magnetic field. The charge is given, its mass is given, the speed is given, magnetic field is given, and the angle between velocity and p vector theta is given. You should find acceleration of this charge. So charge is moving in magnetic field and forces acting on it. Right? If forces acting on something, it has acceleration. But the acceleration is change of velocity. You should find the value of acceleration at this particular speed. Okay, when the speed is this particular value, then what is the acceleration? You can find the force and then acceleration is force divided by mass. So this, when you see this kind of weird-looking circuit, you should be able to simplify it and bring it to a situation when it looks more familiar. This is the circuit. There are a number of resistors and a direct current source. So the value of resistance is given, the voltage is given. You should find the power delivered to this 6R resistor, the power delivered to that resistor. First of all, it looks a little strange, but when you look at it, you can see that 2R and R, these two are connected relative to each other in series. However, the 6R is connected in parallel with those two. So you can kind of simplify this equation like this. This is so this is this 2R, and this is this R, and this is that 6R, and this is. So when you, this is the same circuit, okay? Because 6R is in parallel with the 2R and R, which are in series relative to each other. And this is Y unit, and this is the other unit. Okay, you are trying to find the power delivered to this resistor. So how can you do it? So you can use for power delivered, again, as A and B. Power is current times the voltage, or it's voltage squared divided by resistance, right? If you replace current in voltage over resistance, it becomes voltage squared divided by resistance. Your task is to determine the voltage between poles A and B. That's the voltage on this resistor and also on those two. Okay, you can determine the voltage if you, first of all, you can find the total resistance and find total current. Now the current is the same at any cross section. The current is the same at this upper unit, which is the same as here. Determine total resistance, determine total current, and then basically you get the current between points A and B. Any cross section, the same current. Okay? And then you can find the voltage between A and B. You know current, right? Just determine the equivalent resistance of these three, 2R, R, and 6R. Determine the equivalent, this total resistance of this unit. You know the current, multiply resistance by current, get the voltage between points A and B. Square of that voltage divided by the 6R will give you the power delivered. Okay, now total resistance. This is 2R, this is 3R. This is, and this is. Now let's call this R prime, this upper unit. The equivalent of this 3, let's call it R prime. So these 3R and 6R are connected in series. Right? If you consider, instead of 2R and R, just consider 3R. And that 3R and this are connected in parallel. Therefore, we are using the inverse law. 1 over R prime is 1 over 3R plus 1 over 6R. So determine that the resistance of that upper unit composed of 3 resistors. Now, what is the total? R total is this R prime. From here to determine R prime, determine the inverse and take inverse of that, get the resistance itself. This R prime plus R, this is the total, right? Because this R is connected in series with them. Determine R prime plus R, total resistance. What is the total current? Total current is total voltage divided by total resistance. That is the current in this resistor, and also the current between A and B. What is the voltage between A and B? Let's call it B prime. For VAB, this current, total current, times R prime. This is multi-step problem, but at least one or two should be noticed. Okay. This is better than nothing. Can you see? All this. Okay, simplify the circuit like this. Determine total overall resistance. Determine total current by dividing voltage by that total resistance. Now you know the current in this unit. Okay. Now determine the total resistance of these three. Current times the resistance gives you the voltage between A and B. Now that voltage squared divided by this resistance is the power to deliver to that resistor. Okay, consider this circuit when there's a switch. The switch can be turned to position 1 or position 2. What it says, the value of this resistance is given. Okay, and the voltage is given. And no, the resistance is not given. What is given in part A is the voltage is given, and what it says is at position 1, where the switch is connected to position 1, this way the current is 2 milliohms. So what is the resistance? Okay, current is given, and we know that the current is given by voltage divided by resistance. So all we need to do is to determine total resistance of the circuit at position when the switch is at position 1. When it's at position 1, the current goes from the source, from the battery, it goes through R. Okay. And now, how the current would go? Would it go through this R, or it would go from this point to this point? Here there's no resistance and there's some resistance. Total current would go through the wire. There's no reason for current to go through this resistance. Okay, it would go straight through the wire, 1 R here, and it would go through this R, and then it would go back to the battery. So the total resistance at position 1 is 2R. R total here, R total is 2R. Okay? So you get this V divided by 2R, and then 2R is V divided by R. So you need to determine how the current would go, and therefore you can determine the total resistance, and from there you can find the resistance. And part B says, now you know the value of the resistance. If the switch is at position 2, find the current. You know the current when it was at position 1. Now when you switch it from 1 to 2, you should find the current. Again, you are using the same formula for current. The voltage stays the same. However, obviously, the total resistance changes when you switch it from position 1 to 2. Again, the current would go like this, and it's at position 2 now. At position 2. So there's no way, this is open now. The switch is at position 2. Current cannot follow that path 1. It would go 1 R, it would go through this. Second R, it would go to this point, and from this point it would fork current would divide into two parts. So what is the total resistance of the circuit at position 2? R plus R, okay, that's 2R, and plus equivalent of these 2R's. So you can use, these are in parallel, you can use the inverse rule for these 2R's in parallel to find that the total is R1 When you use the inverse law, you find that the equivalent of these two, which are parallel, is R1 So basically R plus R1 2.5 R. At position 2, total resistance is 2.5 R. For part 2, replace this total resistance with this voltage is given. Your task is to determine the equivalent resistance at position A and position 2. So you have a rectangular prism, which is a conductor, and the dimensions of this are given, two sides and the heart are given. It's connected to a battery with certain voltage, and the resistivity is given. You should find the current. Okay, all you need to know is determine total resistance of this thing. Okay, this is the height or the length, you can call it length, divided by area. Area is A times B here. Find total resistance and determine the current using Ohm's law. For certain arrangement of so find the equivalent capacitance. For capacitors, the rule of capacitors is opposite. For resistors, series resistors, direct addition, parallel resistors, inverse law. For capacitors, it's the opposite. If they are in series, like these two C, C and this C, they are in series, you can find the equivalent using the inverse law. This is stepwise. Find the equivalent of these three. Let's call it C equivalent 1 is 1 over 2C plus 1 over C plus 1 over C. Okay, then find the equivalent of this. Then this and this together are, then find the equivalent of this, which is C equivalent 2 is C equivalent 1 plus C. And then you have 1, 2, 3 again. So you can divide it into convenient groups for which you can do it easily. Determine the equivalent of this group by these three. And then replace this by 1, which is this particular capacitor. And then see this is in the parallel with that C, parallel direct addition, simple addition, you get that. And then you have 3 capacitors in series, again use the inverse rule to find the total equivalent capacitor. So this is a logical question for which you need to know the formulas. The capacitor is charged, totally completely charged by battery, and is disconnected from the battery while keeping the total charge. Now you are changing the distance between the plates. So what is happening with the charge? What is happening with the potential difference between the plates? The field in this capacitor and the capacitance. So what is happening, for example, it says when D is decreasing. So you take this capacitor and let the distance separation decrease. The plates come together closer to each other. What happens with the with the charge. So this is, first of all, one thing you should know. The charge is not changing, it is separated. It's separated, isolated. So there's nowhere for the charge to go. The charge stays there. So what is happening with the field when separation changes? This is the formula for the field. It should be in the but it doesn't matter. The thing is that the field does not depend on separation, right? The field does not depend on separation. The charge divided by area per plate divided by epsilon 0. The field is constant. So the charge is constant and the field is constant. And this helps you to determine the other things. So what is the potential difference? The field is potential difference divided by distance. And this is the potential difference, field times distance. If this stays constant and this decreases, then potential difference decreases. If separation increases, potential difference increases, and then you can come back to the capacitance and determine what happens with capacitance. This is constant. If separation decreases, this decreases, capacitance increases. So basically what we need to know these three formulas, and you immediately see that the field is constant and the charge is constant. And by knowing this formula and this formula, you can determine what happens with potential differences and capacitance. Okay, this is, we have two spheres, one smaller and the larger. The smaller sphere has a charge Q distributed on its surface. The larger sphere has this capital Q, which is different charge. So if you consider a spherical surface in between smaller and larger, this is a dashed spherical surface. What is the field at this point? It says radius R1. What is the field here? So you can use the formula for electric flux. Electric flux is enclosed. If you have a closed surface, certain charge inside, electric flux across this surface is that charge divided by epsilon 0. But also for flux, you know, it's electric field times total surface area times cosine phi, where phi is the angle between magnetic field and normal to the surface. That angle is 0, cosine phi goes away. So from here we can solve this for electric field. Enclosed charge divided by epsilon 0 divided by A, and A is 4 pi r times 3. The surface area of a sphere. So what is the enclosed charge? Enclosed charge is that lower case. Basically, the charge, capital Q, does not play any role. The whole field is determined by enclosed charge. For this dashed sphere, the total enclosed charge is that lowercase q, which is on the smaller surface. So the external charges do not contribute to the flux and to the field. Otherwise, it's very simple. In other words, if something is given, it does not mean you necessarily have to use it. When you do this, you say, hey, I didn't use this capital Q, then it's wrong. No. Just make sure that you are doing it correctly. Sometimes something is given that we are not using. This is the last one that I do, and this is about something that we have done several times. We have three charges, these 1, 2, Q1, Q2, and Q3. All distances are the same, L here, and vertically it's also L. L is given, Q1, Q2, Q3 are given. What would be the kinetic energy about Q3 when you let it go? Initially you keep it, and then you let it go, it goes to infinity. What is the kinetic energy of that charge infinity? By energy conservation, initially there is potential energy, but no kinetic energy. At infinity there is kinetic energy, but no potential energy. Because potential energy is inversely proportional to distance. At infinite distance, potential energy becomes zero, and therefore we can say initial kinetic energy equals final potential energy. Final kinetic energy equals initial potential energy. And the potential energy of a charge in a field equals field times charge. And the field is given by k times q divided by distance. This is the total voltage at this point here. Okay, this total voltage is created by this charge and by this charge. And for each of them, this is the formula for V, for the voltage, k times charge divided by distance. Distance from this charge to this point, right? This is air, this is air, this is squared root 2 times air. For distance, we are using this. For field created by Q1 by Q2, it's additive. This is total voltage multiplied by that charge Q3 gives you its initial potential energy, which is totally converted to final kinetic energy. It's the same. Once you find initial potential energy, you are done. Now the same is final kinetic energy.